various avenues which, in addition to electrolytic cold fusion and in general to fusion in samples loaded up to a very high chemical potential of deuterium exist. These are additional avenues. In the electrolysis of water or heavy water, we have a equilibrium EMF of the cell, about 1.54 volts. The stored work is U0JT, given by this expression. And it's not included into consideration in the accounting in the case of open cells. U, capital total applied voltage. The work done by us on the cell, if we don't include the stored work, has this expression. In addition, we have ohmic dissipation and work against the overpotential delta U, which is the difference between, in isothermal conditions, this difference between U, the voltage that enters to the cell, and these two terms. Here I show a scheme of the electrolysis cell and the thermoelectrochemical effect on the example of a platinum palladium cell. This effect consists of the presence of two heat currents or two additional energy currents not reflected in the product EH integrated over the surface. A here is a calorimetric surface, adiabatic surface, we call it in theoretical physics. We notice that whether the intersection here happens at the 2D electrodes or further out, there are quite different energy constellations that have to be done. In addition to the energy that has been taken into account so far, we have to sort of include these LTA type heat contributions. The correct expression of the energy current density contains the term mu over J, which has usually been taken into consideration. This is in fact voltage between the electrodes times the current. Contains the thermal conduction part, which has been under control also. But it also contains this part here, a Peltier coefficient times the current density. Physically speaking, this represents a kinetic energy and binding energy contribution of the electrons, which is different in different materials. We can say that the electrons carry some heat in their backpack while they come in, and or while they get out, and the amounts are different. The electric current density, on the other hand, is given by Ohm's law and by a small The components of the applied voltage are spelled out on this view graph. We see again the applied voltage is divided in general when we don't have necessarily isothermal conditions into the electrochemical equilibrium EMF, the overpotential, ohmic loss, and the Seebeck EMF. The overpotential is given by the Tafel law, as you see here, in the limit, which we call the reversible limit. This represents a linear expression, but this corresponds only to extremely small values of the overpotential, which one gets, in fact, in the limit where the current density gets to zero. So this expression defines the overpotential as an implicit equation. We can solve this linear one here easily. This one here has to be solved graphically. It gives us the overpotential. It tells us that in the limit of low and really low current densities means close to reversibility, or in the reversible limit, in fact, this overpotential goes to zero. The efficiency of the implied thermal engine, so this is what we find here, is that all electrolytic cells work like heat pumps. This efficiency is given by the work done divided by the heat consumed. And this gives us, the work done is against the overpotential, against the ohmic losses, and against the Seebeck. This one is the only reversible one. And the heat input corresponds to all these inputs here, and the term Ts also. In the reversible limit, we have the ideal thermodynamic heat engine efficiency, as you see here, which goes to zero when T minus T0 goes to zero. As a heat pump, we need to use 1 over eta, and that goes to infinity. This means an infinite number of joules can be brought in the reversible limit into our cell if we spend 1 joule. For each joule, we can get an infinite number of joules in. In the open cell language, the thermoelectrochemical excess heat fraction is given by this expression. It's actually the excess heat divided by the heat we would be expecting to be developed there, or the energy that we have expended in addition to the stored energy. If we include this is a detail, it's a very small difference that comes along with it. If you also include the Thomson effect for the interval between the interior of the calorimeter, surface A on that graph, and the external world. If we introduce also the Thomson heat, then actually what we need to do is we multiply this result here by the ratio between the average temperature between outside and inside. This means what would be in the middle of the insulating wall of the calorimeter, that's the T average, divided by T on the hot side, that's inside. And this is therefore the most important expression that I bring you to when T minus T0 goes to 0, this means, particularly in the flow, in the mass flow regime, we can get that. We can have very small temperature differences, we measure them very accurately, and we get enormous amounts of heat. And so it can go to infinity, and due to this situation, we can get it arbitrarily large. In the case of a closed cell, the gases recombine inside, and therefore we have to include this also. We get an artificially small excess heat fraction. It never can get to infinity because we divide here by a constant reversible quantity U0 also. If the leads leaving the calorimeter are made of the same material but are not at the same temperature, we still get an effect. And all formulae remain correct, just replacing the Peltier coefficient, pi, which is the difference between the Peltier coefficients in all these formulae of the anode and the cathode, by the sum of Seebeck and Thomson coefficients times the temperature difference. Sum and Thomson, so the sum is always between the differences that we get in Seebeck and in Thomson coefficient between the two electrodes in general, but in this case they are made from the same material, and so this is the common value that they have times the temperature difference. Many experiments have led to no excess heat. Those unfortunate researchers, we know for sure, must have used the same material in the calorimeter leads that exited the calorimeter and have also the same temperature. On the other hand, in the other case, we do not know how much is true excess heat, which means how much really came out. Here is an example for some couples. I have 5 minutes. Pairs of electrodes. Platinum, palladium, iron, nickel, platinum, nickel. We see that we get about 2.96% excess heat. In the first case, we could get 24% or 26% in the open cell arrangement. An open cell arrangement, which of course is a set of difficulties. Just think about the internal energy of the gases that leave. It can be quite dependent also on the vapor and so on. But if we make abstraction of that and imagine that we have a perfect way of accounting even in open cell, then this is very similar with various results that are obtained experimentally. In particular, I'd like to mention that my main thesis is that a considerable amount, a large amount of what we measure today is opportunistic heat of this type. For instance, here we look at the initial, we look at the data published by Bonson Fleischmann originally. We noticed that immediately we can derive a constant Peltier coefficient of 390 millivolts, as you see it here, from their data. And this is just an insert of their data, but it can be generalized. If you look at, there are hundreds of examples where we have this characteristic proportionality of the excess heat with the total quantity of electricity that passes through the cell, or proportionality of the excess power with the current. example here from Nagoya, from the Nagoya conference, right at the beginning of the book. If you open it, the first article, you can see how nice this proportionality is. And you can immediately calculate the PLT coefficient of 0.15. That's half of what Olsen Fleischmann had on the previous graph. 0.15 volts, just half, a little bit less than half. It was 390 millivolts, and it's 150. What I would like to say is that, sure, I believe we need to be very careful in all these experiments. Here I give a table. What's interesting is not these values in millivolts that are somewhat are considerably smaller for the pure metals, but it's known that in the presence of impurities, these change by 2 orders of magnitude right away. Even if you only have traces, they can change by 2 orders of magnitude. For semiconductors, the range is about 300 millivolts, positive or negative. These are, I can give you many examples of semiconductors. They have very high values of the Peltier coefficients. I try to hold this customer. Other avenues include that we have to look at, but we shouldn't neglect it. While I want to say that each of these alone, electrolytic fusion, this one here, and the next one I'm going to show you, independently, I think, are just as promising, if not more promising, than what magnetically confined fusion or inertial fusion, in my opinion. Here, in this discussion of the neurocatalyzed fusion, I bring right now nothing original. Whereas in the next few graph, I will discuss the heavy thermals. I have mentioned some aspects also of this, also at the Salt Lake City and Utah conferences, the only ones we had in this country. What I would like to mention is that the effective mass in some so-called heavy thermal compounds is more than 100 times larger than the free electron masses. We can easily have masses larger than the mass of the muon. However, they are all at small wave vectors, and what's important for catalyzed fusion is the region of large wave vectors where the mass approaches the free electron mass. So it looks like we can't do anything with that, but is it really so? We can see here that the heavy fermions, even when we speak only about these metals which are not rare earth except for these, but there are other special ones, tell us right away that those materials which are hydrogen absorbing have a much larger effective mass. In spite of this argument, theoretical argument which I just mentioned, these are hard experimental facts. Whereas these here that are hydrogen rejecting have about the effective mass equal to 1 electron mass if you make an average. So my conclusions tell you that first, the cold fusion approach is most promising. Second, electrolytic cells are heat pumps. We have to take into account and subtract. The thermo-electrochemical effect must be included in electrolysis energy balance. Even when the carbon needs are of the same material, we have to be careful of temperature differences in there. Open cell excess heat fraction goes to infinity in the small chain motor density, means the first limit. This obscures the true excess heat. The smoke screen, I hope, was removed with this observation I bring in here. This effect I discovered around the 1st of November 1992. And due to the lack of cooperation of reviewers, this paper is lingering at Fusion Technology for over a year now, and it hasn't been published. The experimental excess heat is proportional to the total charge. The total excess power can be non-uniform in time. That's very important to emphasize. Due to the presence also of the solvatation energy, and therefore one has to take the total duration of the experiment into account. This means there may be bursts of energy, and at the same time you notice right away how the cell voltage goes down, because obviously the deuterium runs out of the lattice, so the mu is reduced, and I think so we have to be very careful and consider the whole experiment from the beginning, because steadily we have small amounts of excess heat smuggled in and used in order to compensate the negative solvatation energy at high deuterium concentrations, and then suddenly it is released. So it depends on all these effects and on all these parameters here. And all three directions in which you should be considered, actually four if I include also methodology of isolations. My own experiments, I can't tell you much about them. We need to do with their birds. I worked on serum tapper seeds, for instance. Thank you. And I would like to thank you very much. I would like to thank the committee in particular, Mr. Passos, for including this paper.
Thank you very much. So we're running very late, but I think there probably are some questions about this paper. So if we have time to entertain a few.
What was that voice?
Okay. So if you make some blade with the gold plate, it's possible to discriminate which feedback effect is on.
If you make a blank, it means
gold plate,
H2O. H2O means blank. I didn't understand the question. Sorry. Blank can mean many things. It can mean that you want to run the experiment without an electrolyte, just transforming it into a thermocouple. It can mean that you, please explain your question. It can mean that you would like to run your experiment with H2O and no deuterium present.
It means I just substitute the palladium plate with the gold plate, and all the other things are the same.
Means the cathode, both anode and cathode are made from gold, both of them. Yes.
Just cathode from palladium to gold. The only difference in the experiment.
But then still you have the effect if you don't change the anode also.
The anode is always the same.
Platinum.
Yes, platinum.
And you use gold or zero, still you have an effect there. You will have excess guaranteed excess heat. I can calculate how much it is.
Yes.
I could.
Can you
Perhaps we can carry on this discussion later on. It's getting
Yes, the important thing is that we focus on the true excess heat, and we therefore use the millions of dollars that are
tell us about it.
Yo.
About that.
Good.
Okay. Thanks very much, Ed, for the introduction. I'm going to continue where Martin Fleischman left off this morning in describing another form of analysis, one of the simpler ways of analyzing data, calorimetric data, and that is the analysis of cooling curves. We've always used this technique back to 1988 for various sorts of tests. We've not used it extensively for determination of excess heat until recently. In those early analyses, however, it was clear that there were marked differences in the cooling curves, the rate of cooling of cells that had palladium electrodes with V2O and palladium electrodes that contained H2O or any cell which contained platinum electrodes. In general, the systems containing the palladium deuterium or V2O electrolytes would simply have a cooling curve which became much slower than the others. And more recently, we have brought this analysis to look at what is known to us now as heat after death. In other words, the continued generation of enthalpy or excess enthalpy after you have disconnected the power source. In other words, whether you have very low input rate or whether you have no power input. And then we've undertaken to analyze more of our old data sets as well as new data sets with this protocol. We can go back to a point last year, at last year's conference, subsequently in a paper which we submitted and was published in the Physical Letters A, where we had taken cells to extreme conditions, and in these particular conditions we were trying to demonstrate the excess enthalpy which you would observe at or near the boiling point of the solution, in other words, extreme conditions. And in those experiments, we showed that in some cases, in one cell, we showed in that set of experiments, that indeed after the solvent had all been evaporated out of the cell, in other words, the cell was dry, there was still a long period of time after the power input was essentially zero, that the cell still generated an excess enthalpy. Is the analysis of these decay curves, the curves after the shape of the temperature time curves after the power has been disconnected, we will address today. Just briefly, to be short on time, Martin showed this morning that our model of the calorimeter, which we've always used, in the case of a cooling curve, the second, the fourth, and the fifth terms, which are all related to enthalpy input, of course, will disappear, which greatly simplifies the equation. And of course, in the situation with where we have no excess enthalpy, the equation is considerably more convenient and indeed has an exact numerical solution. So the equation is reduced to the top line, which is readily solved to get equation A, where the y is given by the temperature difference between the cell and the bath divided by the bath temperature, and the this as a modification of new installed cooling, modified for a cell which is relaxing by radiation instead of radiation, relaxing by conduction. So we have several different sets, several scenarios for investigating heat after death. These can be when the cell is still full of electrolyte and simply terminating the current, or reducing it in stages. The cell operating at some intermediate temperature, such as 50 or 60 degrees. And you reduce the cell current in stages, 10, and start dropping the current from, say, 500 milliamps to 250 to 125. Or when the cell is full, and you set the current to 0. In other words, reduce the current immediately to reduce the enthalpy immediately to 0. Another alternative is cell full, cell operated at the boiling point, and then start reducing the current, or having the cell full and operating at the boiling point and set the current to 0. And another set of possible scenarios is allowing the cell point to dry by at the same time maintaining the well voltage of the potentiostatic. And under these circumstances, which are representative of the data I showed you just a second ago from last year, you have a very small, if not 0, enthalpy input, a very small current at that point. And the final scenario is the cell being allowed to boil dry and simply disconnecting the potentiostatic from the galvanostatic from the cell. And of course, there are many intermediate cases. One, for instance, if the cell is partially filled, you have more complex scenarios. We won't address those today. They certainly can be analyzed. A typical relaxation curve in that equation A that you saw just a minute ago is shown here. These cells are essentially blank or blanks or near blanks. In other words, I think Mike McHugh mentioned this morning, the best blank to study in general is a palladium electrode, which does not work. And I think that is the upper curve, if I remember correctly. There is a slight curvature in that curve, which is sensitive to the very small amount of heat that's in that cell. It's only just a few milliwatts. Whereas the other line is the bottom curve is a plot of a cell with a blanket. Is this platinum? That's platinum beads. And this curve, you see, is a straight line as expected. And from the slope of that line, you determine you'll have a value of the heat transfer coefficient of that cell from independent calibration experiments, and you can certainly derive an accurate value of the heavy water content of the cell from that slope that you saw from the equation. So let's look first at some data. This is based on scenario 2. These are individual points for the cooling curve. This is the coordinate which we talked about just a minute ago, plotted against the time. And again, you get a straight line. This is almost a blank. It's a palladium cell, a 4 millimeter palladium electrode at 1 molar LIOD. And at an intermediate temperature, this is scenario number 2, an intermediate to 40 to 50 degrees. The current is simply switched off. It's totally switched off in the cell. And if we apply if we apply the method of data analysis, we can do detailed thermal balances as given by equation B. We can do this point by point, which in essence means that you're going to be differentiating the data, taking the difference in the temperature between the two times. And then in that case, if you treat the data that way, you get an absolute value for the excess enthalpy as a function of time, and you get an absolute value of the rate of relaxation of the cell, the enthalpy, the radiated enthalpy output of the cell. And if we do that on this particular data set, which is a near blank, but with the point-by-point method, we can see that we get, I'll show you for a second, the QF measured by this technique starts at the order of about 20 milliwatts after you terminate the current and comes down quite rapidly. And the important point here is that we get a very near thermal balance after a short period of time, which is on the order of a few tenths of a milliwatt. You observe thermal balance for this blank. This represents the very small amount of excess enthalpy that was present initially, and that then can be completed by looking at the cell potential. This is a rather important point in this case. And as you will see, the cell potential when the current is turned off goes very rapidly to zero, and maintains that value throughout the rest of the experiment. Of course, the power supply has been turned off. The cell difference between the voltage difference between the two electrodes in the cell, which still contains electrolyte, 1,1 or LiOD, falls from its original value down to very close to zero in just a few minutes. To further the analysis, to make it a little bit more clear what you're looking at, and go to an integral method rather than differentiating, rather than taking the differential of the data, trying to get at the absolute values, which of course also expressed in rates. We can integrate, as Martin mentioned this morning, all of the various terms, and in that case, we will then be looking at the energy, which is more meaningful. Instead of looking at the rate of change of the enthalpy content of the cell, we will then be looking at the total enthalpy due to the contents of the cell. We'll be looking at the total number of joules of excess energy that's been liberated during the entire experiment, and the total amount of heat that comes out by radiation. If we do that on the same set of data, we get this figure, which is the integral of the radiated heat output. That's the total energy that's coming out due to the contents. Due to the radiation in the cell. And that comes out to be on the order of 14 kilojoules. And if we do the same thing to the excess enthalpy of that experiment, we get an excess enthalpy. You notice there's a difference in scale here on the right-hand side. The difference in the integral of the excess enthalpy now is only the order of 300 joules. So this was a very small output under these particular conditions. And if you assume that that's, if it stays 300 over that entire term, which it's not on the maximum generation rate, there would be something on the order of about 7 millivolts, but that clearly could be determined. In order of time, I won't show the additional data for this cell. Again, we're talking about this is a 1 millimeter by 12.5 millimeter palladium electrode D2O. This set corresponds to scenario 3. This is a cell that's been taken to the boiling point. And as it begins to boil, we now disconnect the power totally to the cell and look at its relaxation curve. So this is the relaxation. This is the same logarithmic coordinate which we looked at a few minutes ago. This represents the straight line represents the expected decay of the cell, the cooling rate of the cell. So you see the cell is cooling along this region. Then the cell starts to heat up after some period, after some 15,000, 20, well, on the order of a few thousand seconds it starts this. So there's another source of enthalpy in the cell, preventing the contents of the cell from cooling down fully. And after some long period of time, in this region, there's something on the order of about 20 milliwatts being generated. Along here, the cell then is allowed again to, or then begins to cool down again, and will continue to do so until it's down to bath temperature. Now, in that experiment, we get about 15.5 kilowatts, 15.5 kilojoules compared to the 14.2 kilojoules we saw on the last slide, because the previous slide had slightly less water in it, In fact, this one was taken to the board. That cell, the previous cell, has a smaller amount of water in it than this particular cell did. But the QF, the total QF integrated excess heat generated in this experiment was 3.2 kilojoules, about 10 times that in the first cell, and now represents about 1/5 of the radiation rate. During the rest time, I mentioned what the generation rate was in that short period of time. But anyway, you get about 10 times the heat out of this particular intermediate cell. So rather than go further with that, let me move now to the more extreme condition. But the the main point of this slide is that you saw that in a near blank you get almost a straight line decay, predictable, very predictable result, just due to the cooling curve, the normal cooling curve. In the intermediate case, where you're generating more excess, where you're generating clear amounts of excess enthalpy, there's a break in the curve, there's a period of deviation, strong deviation from the normal expected relaxation curve, and after that it begins cooling again. If we go to a more extreme case now, we let the cell go to boiling and let the voltage be maintained at the rail, in other words, the compliance voltage, not the compliance voltage, the maximum amount of power, the maximum voltage that the power supply can put out. Then you see something like this. This corresponds more or less to one of the cells, or to one of the cells that was described in the first image that I showed you. So there is a market region here where cooling does not occur at all. This is where the major portion of the excess heat is generated. Then it approaches a cooling cycle, or starts to cool along the predicted slope. It then goes into very erratic behavior, again, proceeding along the line and then going back at the very end, some orders of magnitude down that road to go into a more predicted cooling mode. So at long times, we can we'll just look at this center section here where we have the data points plotted. We can then look at the point-by-point method, and this is the excess enthalpy generation during that latter period, still coming down. We then see that it's flattens out, it comes up again, and there's market deviations of excess turning off of the excess enthalpy generation. And then finally, at the end, it goes to the value of 0. The cooling rate is shown in this slide. This is the point-by-point cooling rate, the absolute cooling rate in watts. As you can see, as excess enthalpy is generated in the cell, there's a corresponding decrease in the cooling rate. The cells are going to be, in fact, at this 1 point, 24,000, you can see there's a sharp rise in the cooling rate, which then relaxes back down again which strongly indicates a source of excess energy generation in the cell at that particular time in the cooling curve. The best way to, again, to represent that is to look at the integral representation. In this particular example, we have the total energy generation. This is the total enthalpy generation due to radiation in the cell. This time is on the order of 128,500 joules compared with the 14 or 15,000 joules we saw before. And the change in the enthalpy content of the cell, which is on the order of 6 kilojoules. This is somewhat overestimated, however, due to the fact that at the end, all the liquid is gone in the cell. We assume a value of 82 kilojoules, which is really about 50 kilojoules, so we overestimated by 5/8. So this number should be somewhere on the order of 4 kilojoules. But anyway, there's clearly an excess of 128 kilojoules generated in this cell. We can only, in the way this particular experiment was run, the current was monitored down to 1 milliamp, so that we can only guess the precision of, or the accuracy of the current generation of the cell, even though the cell is dry. At this point, the maximum current that could be flowing in the cell is on the order of less than 0.499 milliamps, in which case the interval of that would be an entire period of time could only be on the order of about 1.7 kilojoules. So even at that, the total estimated excess that we generated at this time with very little power, then it's on the order of 120 kilojoules. That, of course, would translate to about 10 megajoules per mole per atom of palladium in the cell. The point is there is a strong excess of energy generation with no power in at that point. It's important to look at the very last bit of that curve. This is very near the end. You can see that, or near that corresponding period near the end, right? So this is the expected cooling rate. You can see that it's continuing to cool down. And if we superimpose now the cell voltage, the measured cell voltage of this cell, remember it's dry, there is electrolyte in the bottom of the cell in the form of a solid mass of solid electrolyte. The thing to remember is that in the previous cells, this voltage came very sharply, increased to zero very sharply. There was no remaining voltage in the cell, even though the same materials involved. If you drive it to extremely high conditions, however, when it's been held at very high potential for a long time, very little power input into the cell, we see that the voltage of the cell does not go to zero. In fact, we observed previously that this may be held there for only over a month. So the question is, we have a platinum secondary electrode in the cell, a very large area, so it's not polarized. It's a large area compared to the size of the cathode, so the palladium electrode is certainly not polarized. Therefore, the platinum electrode must assume the potential of the cell potential must have been adjusted to the potential of the material in the palladium metal. And of course, this is on the order of 1.2 electron volts at this point, which is a huge amount of energy. And the question, of course, is what is the situation which leads to having such an extremely high potential of the material in the lattice. Now, we talked about that before. Conclusion was pointed out essentially in the original paper, in that the conditions we were describing in 1989, i.e. higher temperatures, you had to achieve higher temperatures in order to be able to generate higher rates of excess entropy. We clearly did not know what would happen when we did that. So we have to be very careful in these experiments. We still maintain that. And we, of course, looking at higher rates of generation, designing experiments to get higher rates of excess entropy generation. So in conclusion, if you have no heat generated in the cell, cooling curves will show very cooling curves in which the power is interrupted either by totally turning it off or turning it down to very low levels. Will give predictable curves, straight line plots of the particular coordinate in the derived model that we've always used. If you have a little bit of heat, it's easily seen. Small amounts of heat is measurable. However, it does not severely distort the curve, other than the fact that you see these large breaks in the curve. But however, if you have high heat generation, you have enormous deviations in the cooling curve, still showing a split between the two cooling portions, clear many other effects that take place at the same time. This is characteristic of our cells. Thank you very much.
Thank you. Are there any questions?
Yo.
Just briefly, the scaffold that maintains itself receive for 3 hours.
It's 100 degrees.
You're asking on that, that's about a watt. And was there a thermocouple attached directly to that cathode? How was the temperature made?
The temperature was made in the gas cathode. So we're still located in the same position in the cell. And then we have the maintained generation early on is 8 watts.
I would like to suggest that this very valuable calculation and experiment be completed by taking into account the heat of desolvatation and comparing these two and seeing how much heat remains unaccountable these are the raw data, but it's very important to know after that how much material came out of the cathode.
Right, in an electrode that size, if you have it's fully loaded, given it is fully loaded to a hydrogen or deuterium to palladium ratio of 1, then you would be looking at the order of 360 joules or something like that order. Total, that would be the combustion of the hydrogen. If you were to combust it all, that would be a maximum of 360 joules. The heat of absorption for that amount of hydrogen is probably
It
much
was
less than that. But if you combust it, if you burn it,
what are the amounts
well, the maximum it could be, and
that you got here on the other?
we don't measure the maximum.
The total amount.
The excess.
If it is like 1,000 times more than the total that you can get by burning all that hydrogen,
That's about 1,000 times more. It's 120,000.
So it's 1,000 times more than
1,000 times more than the combustion energy of the hydrogen is just present.
Even so, it would be very good if it's included there and calculated in the same paper and subtracted, and then let the rest let
I
miracles.
think we're talking about millijoules, gigajoules.
I don't know.
It's the wrong sign anyway, yeah. We'll just add to it. It's the wrong sign.
I mean, the energy of the hydrogen that's in the cube has the wrong sign in the sense that you have to subtract it from this energy that's coming out. But
We have to add it to the thing.
well, it's endothermic at the beginning. When you put in deuterium up to a certain point, I think about up to 0.7 or 0.6 or something like that. But later on, it's endothermic when you put it in and exothermic when it comes out. See, that's the point. Yeah, I have the impression that you're not aware of these points.
But I think Martin showed this morning, what we're trying to do is the ratio, the loading ratio is higher and higher, you drive the heat of absorption to the end of the
Yes, right. So when it comes out, then it's exothermic. So we have to subtract it from what you have now. That's what I would do.
Perhaps we can carry this discussion on later and get some more questions. Steve Jones?
Thanks. Two questions, Stan. First of all, your last slide indicated ignition. Are you claiming that this heat is due to fusion reaching an
I was trying to say that the voltage of the deuterium and the palladium is only 2 electron volts.
The question is, are you claiming ignition to explain this 100-degree centigrade constant temperature for 3 hours? That was the term on the slide you showed last slide. In any case, are you claiming fusion ignition?
I'm claiming in excess of the generation of that experiment of 120 kilojoules.
Well, is it fusion ignition? Do you claim or not?
We still claim it's 300 times larger than the chemical reaction.
No, the question is it due to fusion ignition? Yes or no? It's a question. Is this heat that you claim due to fusion ignition?
It's due to a nuclear reaction in the metal. Between the deuterium. I'm not saying anything about it.
You're not saying it's about fusion.
I'm not saying it's conventional fusion. I'm saying it's due to a nuclear reaction in the metal system.
Okay. Can you explain why it's 100 degrees as opposed to, ramping up if it's
It's a function of where you do the cooling curve. It remembers the temperature, which is where it's taken out. I suspect if you go to higher than that, higher temperature temperatures, then actually won't be 100 degrees. It will be some temperature higher.
Now finally,
And we have seen deviations. We have seen it get hotter than 100 degrees. We have seen it get cooler than 100 degrees. The particular examples we showed
That's 100, yeah. Now, with the light water stand, you said you had boiling. Is there excess heat in the light water case? No. No excess heat, but you do get boiling.
I'm sure you can boil. Sure. What you do is put enough power in. What really happens in the boiling steam is that as the cell starts to cool, you keep boiling the water out. Okay, you're boiling the water out. You will find the resistance of the solution increases. Okay, you will find the resistance increases to the point where the power supply, or whatever you're using, then it starts to drop. The output power will start to drop because you get against the weight, you get against the control, you get against the point at which you can maintain the current. So the current will start to fall in some cases with water. The current will fall so much that the cell just stops boiling.
Do you have film boiling?
No,
Anywhere else? No film boiling.
In fact, the solution stops boiling if you have water because the resistance in the residual solution increases to such a point where current can't flow through the cell anymore, and therefore the boiling just stops. It cools down. You end up with several cc's or several tens of cc's of water left in the cell. That doesn't happen with palladium. The rate of excess input regeneration so fast it blows it evaporates it all at very high temperatures very quickly. You're not left with anything else inside. So you have this dry cell, which we've shown you in the video. But with water, that doesn't happen.
Well, we've done it with water still.
Well, if you take it up to several thousand degrees, I mean, probably good.
Around 1,000, it stays at right near 100 and boils dry. We've done it with
It
the
boils up, yours boils up. Well, it's a matter of rate. I mean, you can certainly put enough electrical energy into any cell. This is just a teapot to boil it dry. There's no problem with turning the stove up and boiling it dry. And that's all. It's the rate at which that happens at a common power. If you put the same amount of power into it, there's no obvious reason why once you boil dry 2 days before the other.
But let me understand. So you're saying with light water, you don't claim excess heat, right? Is it just with heavy water?
Under our experimental protocols, we have not observed excess heat generation with light water.
Okay.
Okay, I think we have one more question over there. Douglas Morrison.
In your March 89 paper or 89 paper, you were talking of nuclear fusion and ignition.
Does this have anything?
If I understand,
Does this have anything to do with the data which was presented in this talk?
you finished your final slide said ignition, and you talked of nuclear ignition. Now, if you use nuclear ignition, you expect to loss of particles. Did you try and measure these particles, and were you wearing film badge to protect people?
We've answered this question every year for 3 years, Douglas. The answer is still the same.
And that's it?
You don't remember?
You mean you do not measure nuclear particles,
Do
and
you
you do not
remember?
wear film badges? Do you wear film badges?
I don't see what that has to do with the subject.
Well, it shows you whether you're it shows you whether you believe whether it's ignition or not.
You're bringing up scenarios which have no place in this discussion.
You said ignition.
Good.
Okay, well, thank you very much. Before you go, I'd like to remind the speakers for tomorrow to come to the speakers' breakfast at 7 o'clock in the room across the hall from this room. I can vouch for the fact that you get a very fine breakfast, so it is worth getting up that early. Thank you very much.
No, it's not. That's going to be later. Yeah, okay.
Somebody asked me about paradigms, what that means. I think it's somewhat comparable to changing your religion. I don't know. Anyway, if you want to get an idea what a paradigm is, see those two video tapes. They're about 30 minutes each. There is one change in the agenda that I make note of, that N4.12 replaces N3.5. I think the rest of them are going to fall into place without any major changes. Of course, in this meeting here, you'll hear about some shifting, but I'll leave that to Sharon. And I'd like to see Ikigami and Smedley at some point mid-morning if I can find them today. Thank you. Come on. Tom Claver is going to be chairing this session, assisted by
Thank you. Good morning. We're going to start off with the food drop and go on to Professor Ghazi and Dale Tuttle. Then after the break, we'll have Chris Will and Doc give the 40-minute talks. So, without further ado, I'd like to introduce Jan, and he'll be talking about these television products and logos of that.
This work was done by mostly by 3 people. First, both and this work was originated in Russia in Scientific Industrial Association. The beginning of this work was when we heard about quantum classroom announcement about creating results. We were familiar with garbage trafficking, radio detector, so we started our work with gas discharge plasma. Basically, it is a vacuum chamber with cathode, anode, and a bunch of measuring instruments. The situation here is basically different from electrolysis because we work better. Sorry. Is it better? Okay. So the situation is basically different from electrolysis because at few torques pressure of the cable, the voltage is around few hundred volts, and it is much higher than the threshold of implanting for all the solids internal diffusion in the material and contamination of the upper surface of the cathode center. So, as I said, we used deuterium, few-torr, pressure. We used a lot of foil cathode, mainly palladium, but we also used zirconium, titanium, and you name it, practically most of the materials from the periodic table. And this chamber was supplied with a bunch of measurement instruments. So it is. It was two silicon surface barrier detector for charge pipe for registration, a few slow neutron counters, helium-3 field with paraffin manipulations, plastic detector which we used as a neutron spectrometer, germanium lithium detector for gamma spectrometry, and on top of that we used a lot of passive detectors such as CR39 polycarbonate glass, which was inserted directly into the vacuum chamber, and extensive studies were made with X-ray films even inside the chamber and outside the chamber. So basically the chamber is a stainless steel tube with from 3 to 5 millimeters walls, but on top of the chamber sometimes it was a grilling window, and it had quartz observation window to control motor discharge. The detector was very calibrated with standard means, or gamma detector was calibrated with various radioactive isotopes starting from grease and cobalt. And neutron counters were calibrated with plutonium beryllium standard 3-peak source. And CR39 and SSB were calibrated with uranium-235 and plutonium-239 radioactive isotopes. We had a lot of measurements, a lot of strange results, so I have shown only some of them. So this is the result of passive CR39 layer inserted in the vacuum chamber here. This is the cathode surface. It was palladium cathode, 100 millimeters thick. The distance from the cathode was 6 centimeters. And the plates were calibrated with plutonium-239 alphas. And here are the results after low discharge experiment. So the input ground is 2 to the 5 centimeters squeeze. And that counting efficiency and time that corresponded to about 10 to the 5 charge particles, considering that it was a point source and 10 to the 5 of 4 kg. results you get very strange. So here is the sum of few tens of experiments. So it is not the actual spectrum, it is just the sum of few experiments. So it showed that most of the charged particles are located in the energy region up to like 6 MeV, but there are some peaks in the region of 12, 16, and maybe even 18 MeV. So these are very strange results. It's not very easy to obtain high energy charged particles. More than, let's say, 10 MeV for this is the thorium isotopes. Here are the results with charged particle detectors with aluminium fluoroscreens. One was 10 microns, another was 18 microns. So from these degrading foils, basically you can calculate the stopping efficiency of the foil and from there the type of the charged particle. The precision of this method is not very high, but from this picture it is judging from the cutoff energy. So here it is, let's say, something around 2.5 MeV. Here it is close to 4 MeV. From this spectra, it is clear that some of the charged particles are very heavy. They are not alphas, but creating the mass of this massively low to lithium isotopes, something between lithium 6 and lithium 7. So as we believe, charged particle results are mostly indicating, they show that something strange is happening in this environment. And as the background radiation was close to zero, it was a couple of counts in 2,000 seconds. The normal experiment time was a few hundred seconds, so the background was practically zero. So these are very strange and very interesting results, as I believe. In another set of experiments, we would calorimeter, it is heat loss time calorimeter, in vacuum chamber. During these experiments, we couldn't have charged particle measurements because it's calorimeter blocked the path of charged particles, but still we could be able to measure neutrons and gases. So the basic scheme of calorimeter is follows. So it is a cathode, here is a massive molybdenum substrate with heat flow measurement device, so there is a space with thermocouple which are temperature gradients. The same thing in anode, and there was a massive copper heat collector insulated from inside with aluminum inside and from outside, and with extensive molybdenum heat screen and aluminum heat screen outside heat collector. From below, this calorimeter was closed with massive quartz plate. This type of calorimeter, of course, it is not very precise and cannot obtain precisions in 1% range, but few percent precision is quite obtainable in this system. Here is the result of friends in pure hydrogen. So this calorimeter consists of 3 parts, and each part has its own contribution in the calorimeter measurement system. So it is the heat measured by anode part, the heat measured by heat collector, by cathode. Here are the sound of both 3 parts. It was well known from literature, but here also the clearly show that most of the heat in this type of the charge goes into the cathode. So the cathode, the heat flow in the cathode is higher than it is in the other 2 parts. As it is easy to calibrate the heat losses for each temperature of each part. So this is the corrected curve of the combined heat measurements. And this is the electric input. So this is current by voltage multiplied by time. And here are the results of the corrected combined heat measurement of the calorimeter system. So looking here, one can see so the precision of this calorimeter is around 10%, and the estimated precision of the calorimeter varied from 3-5% in low energy, so up to 3-5 kilojoules, it was 3-5%, and from 5 to 10 kilojoules, it was about 10%. So here are the actual measurements of the calorimeter. So here is electric input. This is correct?
Can't hear you.
Speak up a little bit. Yeah, could you speak a bit more loudly? I think the best thing is, do you think you could speak a little more loudly?
Maybe I'll... This curve shows the corrected curve for calorimeter efficiency. It is quite clear that the results of the excessive heat measurements are quite high. So it is 2 here, 3, some here, something like that. And the maximum heat input we could measure with this calorimeter was about 10 kilojoules. After that, the temperature of the heat collector was high, more than 100 C, and the instability of heat flows outside the calorimeter, because deuterium has a very high heat conductivity, where too strong and the accuracy quickly run down. So best results were obtained in the range up to 10 kilojoules. To beat chemistry, if you can consider the most violent chemical reaction, so if you burn off the deuterium we have in the chamber and the oxygen, it requires around 800 joules. So, as one can see from this curve, the chemistry can be beaten in the beginning of the experiment. This plot was obtained as a derivative of the previous ones. So this is the power. So this is the electric power. And these are the calorimetric results in this kind of experiments. So maximum power obtained in this was around 30-something watts, around 5 watt electric input. And there is some statistics where we had 78 drugs with caloric diminution. We consider that any results below 10% or related zero. So in around 50-60% we had excessive heat, and the best results were 500% of electric power with maximum of 33 watts of plasma. So as I already told, the situation in VHS is entirely different from electrolysis because we already have a few hundred volts of voltage. And on top of that, we have runaway electrons, which can be the results of overvoltage up to a few kilowatt. So basically, one can expect normal DT flow fusion in this system. And so we were looking for. And as neutron counters now are not immune to electric pickups, we tried activation experiment with silver foil wrap and paraffin. And after the exposition of the vacuum chamber, this silver foil was carried to the end of the room, maybe 6-7 meters from the chamber. It was put on beta counter, and distinctive radiative decay of silver was observed. So here are the results of activation, neutron activation. So basically, in silver, two radiative isotopes are formed with around 25 seconds. Time now 25 minutes, so yes, with something like that. So this is the equation for obtaining with plutonium counter. This is actual results from this is the results from plutonium source and the geometry, considering that all the neutrons come from the cathode. So the intensity was 10 to the 16 seconds, so the best results here are close to 10 to the 7 meters per second. So this is a very high number of neutrons, and we observe this huge number of neutrons very seldom, a few times, but we managed to gauge one of them. So basically, consideration was the basis of normal DT fusion, but when they measured neutron spectrum in this situation, it appeared that it is something else. So it was standard still single crystals with various things. So the thin one can accumulate from gamma radiation. So it's 2.9 million crystal. 500 kilowatts of gas, and in many ranges, you can see. So, basically, so we can see some 2.45 immediate neutrons, which are all of them, but on top of that, we have a big number of high energy gas, and the cutoff energy is lost 17 or something, maybe can be explained on the basis of even DT fuel. So these are very strange results. The intensity results of high energy group of neutrons to low energy group of neutrons. government reaction and treatment will not be reached. So if you consider this to be 1 group of neutrons, this is another group of neutrons. The intensity is very strange. So a normal DD field runs have 10 to the 5, 10 to the 6 elevation of this group. Right here we have something close to 10. So once again, we have some very strange results. This here is a typical gamma spectrum and detector. The background is correct. So some of the gamma lines, the way they were identified with elements, and it appears that most of the identified language, the strongest ones, are the rhodium radiated isotopes. Strangely enough, most of the studies can be considered to be the results of 1 of 5 mass isotopes, very magnified everything in the excited states of palladium 1 of 5. This is the result. Then the X-rays position outside the chamber, so it is 5 millimeters thick steel wall, and on top of that we had 2 millimeters of lead and 5 millimeters of organic, so it looks like organic is multiplying gamma radiation. And gamma radiation has a very strange pattern, so it is something like uniform lightning of the field. And on top of uniform lightning, we have distinctive spots, which can be seen on two successive fields, and huge number of small spots. The blank results no spots, no lightnings. Once again, we have very strange terminated gamma beams, which, as far as I know, can be explained in any same way. We made an extensive studies of materials before and after VHS experiments. Here is an example of palladium material impurities. So basically it is noble metals such as palladium and something else. And the materials we used were
Your particle spectra, silicon detectors are notoriously sensitive to RF power to a large extent. And I was wondering if you used AC or DC coupling, and if you did, what kind of spectrum you got with controls that are such as conductive discharges of argon or hydrogen.
Okay, so this is another thing that we saw very small but nothing and I must tell you that this is a closed system. It is insulated from both. It's insulated with the meaning so blood. shifted energy. And gamma radiation is not consistent with non-neutral radiation. So we have some deviation from microcosm, that's for sure. But of course, I already mentioned maybe not darting, but just run away electrons in a more efficient way to use energy. So maybe we have to
is really important in such a type of measurement is not the revolving power in itself, because basically what we are going to look at is probably a low amount of helium with large amount of deuterium, or with any other mass near a low intensity signal near to a high intensity signal. And this is sometimes called the abundance sensitivity mass spectrometer. It means that your capability to measure some low signal on the tail of the high intensity signal. And this gives you an idea, this is a factor of 10,000 approximately. Did I move it? So, let me recall you what Gersi told you yesterday. Our collecting system, we have a liquid, actually nitrogen coming from the liquid, which floats the cells, goes to recombiners through the palladium powder, getter, and finally there is a stainless steel sampling cylinder, which is the collecting cylinder. We have two different lines, we have 6 different lines, but 2 different types of materials that we use in the lines. On cell number 1 and 4, is all stainless steel, while in cell number 2, 7, 8, and 10, we have nylon tubing. This for some part of the collecting lines, we have nylon tubing. Let me remind you that our cell number 1 is our reference cell, is the blank cell, and number 4 is that cell with the complex electrode designed in order to maximize the capability to charge and to charge the electrode itself. Maybe you remember because we talked about we have in this cell number 4 the electrode. The electrode at the electrode can be applied a second current in order to push the deuterium inside. Here is depicted our inlet system. You see here in the blue portion is the sampling cylinder which has been brought from the basement where the cell isolate is located to the second floor where we have the mass spectrometer. It is connected to an inlet line which is made by the common small KF vacuum flange fittings. And this inlet line can be pumped with an auxiliary diffusion pump so that the gas sample is allowed to expand into this inlet line and to be absorbed by the active charcoal in liquid nitrogen. Actually, what we are looking for in this absorption stage is not to, what we are concerned with is not for the deuterium, because the collecting line has already a lot of capability to lower the deuterium content, but what we are looking for is to lower as much as possible the partial pressure of nitrogen before getting our sample into the ion source, in order to be able to open as much as possible the dosing valve and without deteriorating too much the pressure inside the ion source and so the resolution and the sensitivity itself. Actually, by allowing it to expand, the pressure goes down to 10 to minus 2 torr approximately. And at that stage, before admitting the sample into the ion source, we shut off the pumping into the ion source only. And by taking advantage of the differential pumping of the mass spectrometer, you will have the partial pressure of helium inside the ion source that goes up and subsequently falls down. It's a kinetics, I would say, that is controlled by the
impedance by which the gas is pumped through the field interconnection between these two sections by the pump, which is still working for the analyzer section. So we are not in a dynamic way of handling the situation, and not in a really static way of handling the situation. By this means we have quite a good increase in sensitivity, and on the other hand, we do not have really any memory problems. So this helium time dependence you can see here. Please notice that we have all this to normalize line intensity when admitting quite a large different amount of air in this case into the line source. We have a time scale in order of minutes, so our signal in the line source lasts for 20 minutes. And you can see here that between the dPV and the ppm range, we do have a good superposition of the helium time dependence, so that it's either possible to measure the integral or the maximum peak. Actually, for the large section, a large portion of the experiment, we did it both ways, and the difference was within 2 or 3%, something like that. So let's see now a typical measurement. The time slopes in the vertical direction, while the line intensity rises on the right. The green line is the pressure inside the ion chamber, which is shifted in space, but not in time for the kind of order. So here, before the opening of the closing valve, we are on the helium mass. The signal goes up. This is only a change of the scale, and goes down with the kinetically obvious but you may wonder how we are sure that we are on the helium mass. Well, we actually do a voltage scale number, a helium per watt, so that let's look at this larger portion. We are here before the helium signal goes up, before the opening of the closing valve. We are at this particular number of accelerating potential, so we are on the mass of the helium. We go by lowering the voltage between the deuterium and helium mass, so, and after that we can go in mass with the deuterium and back and so on to the deuterium. So we have the capability to look at the background in that particular moment of the experiment, and we also can measure deuterium, and we also have to check that these two masses are really helium and deuterium. I mean, if we were for some reasons erroneously following the deuterium, we would have found nothing at this voltage, accelerating voltage. But we were going to have ratio of masses up to deuterium, to which nothing is possible to have. So you also see here that after some time, the helium signal number in this case rises again and goes down. Well, we are in this case, we are admitting a known amount of air immediately after the measurement of the sample signal. Let me go back to our apparatus. You see here we have a small volume in the order of magnitude of 1 centimeter. Actually, it's a short tubing which is used to connect the